Okay, hello everyone. Good afternoon. I hope you all are on your second set of coffees and that it wouldn't be too boring and we'll make this fun. I know it's 3 p.m. But with that said, I am Kusha Maharshi and I am a senior software engineer at Bloomberg. Today I'll be talking about how we used distributed trace to generate end-to-end latency metrics at scale. And before I really get into the nitty-gritty of it all, I want to kick us off with a little story time. So I work on the telemetry infrastructure team, which means that our job is to provide observability and monitoring solutions to the rest of the firm through telemetry data. And that means that our clients are other engineering teams. So these teams are building and maintaining trading systems and messaging systems, news infrastructure, middleware, so on and so forth. And with all of these products, they must handle large volumes of super high stakes data with very low latency. And especially in the financial sphere, just even milliseconds of delay or latency can equate millions of dollars lost. And that is why engineers must make sure that they prevent latency from creeping in to these systems. And so they have to monitor the complex distributed systems that actually back the user-facing products. And as a result of that, we saw a recurring request pop up, which was that teams and engineers wanted latency metrics for end-to-end workflows. So for example, let's say we have something super simple like this, where you've got your users making some requests that hit service A. Service A talks to service B, which talks to service C, and then some users receive a response, right? In that case, engineers want to know, well, how long does it take for requests to go from A to C? And that's your end-to-end workflow. So previously, what would happen is either teams would use some amalgamation of service-wide metrics, so your application level metrics, or they would have some custom end-to-end tracking system. So maybe think passing around a session ID or a request ID, some sort of state management that can let you kind of put together requests across different services. But then obviously, with the increasing adoption of, if you didn't already guess it, distributed tracing, we decided to adopt that as the unified, centralized solution for doing this. And very quickly, as our team decided to build this out, we realized that I will actually take a quick pause to do a quick interlude for what is distributed tracing. I know a lot of this crowd might be familiar with it, but if you're not, just going to highlight some salient features, which is, in this case, you see you've got, let's say, someone making an API request, and then a service parses the request, and then, make some calls to a database to read some data and return something to the user, right? In this case, every single little hop in this path is a span, which is uniquely identified by a span ID. And the entire path itself is a trace, uniquely identified by a trace ID. And then you will also see that there's this timeline up top. That is because every span holds timing information for when a certain operation or service call started and ended. And we are here to talk about latency metrics, so these timestamps will be key for what we talk about later. And finally, each span also holds references to its parent spans. That is to say that a callee service will know who the caller was. And that's what you see here in these yellow arrows. So that's a super quick overview of distributed tracing, which of course is part of the Open Telemetry standard. And this standard allows us to visualize the path that requests take through complex distributed architectures. Okay, so going back to my story. We decided to build that, we want to build a solution, but very quickly we learned that our firm's trace data was rich with very complex parent-child relationships between spans, with a lot of long-running spans and traces, and of course was at a high volume of 50 billion and counting spans a day. And we also learned that due to the complexity and scale of this data, open source or vendor solutions would not quite work for this end-to-end metric generation. And so we decided to build a homegrown solution. And that's what we're going to talk about today. So before I get into the technical details, I'll do a quick agenda overview for the rest of the presentation. I'm going to start by sharing an example workflow from the real world. We will then look at what the corresponding trace for such a workflow looks like. And then we will see what it takes to get the end-to-end latency from just one trace. We will extrapolate that to scale, and we will dig into 2 specific approaches for how to do that at scale, and kind of summarize the things that worked for us and did not work for us. And then finally, I'll end the talk, and we'll have time for Q&A. OK, so with that said, let me introduce an example end-to-end workflow. This is from the finance world, and it represents a very contrived, generalized version of what an equity order execution system looks like. If you're not familiar with financy things, I'm right there with you. I'm an infrastructure engineer, so this is also me doing my best. But essentially, in the system, you can think of clients being traders, and think of people like buying, let's say, an Apple or a Microsoft stock. So we've got these orders coming in from our different clients, right? These orders go through what's called brokers. Brokers generate something called a fill message. Fill message, essentially, as the name suggests, is storing information about how much of an order was fulfilled. Then that goes through an order management system, which does the things an order management system does. And then from there, those messages are put on to a Kafka queue. And then we've got this publisher service, which is going to pull messages in batches off this queue and publish them out for users to see. And the end result is traders being able to see the status of their orders on a UI. Now, if there is a delay in viewing the status of your orders, then traders can quite literally lose monetary opportunities. And that is exactly why we need to get end-to-end latency metrics to have this end-to-end latency monitoring so we can ensure a good user experience and prevent these delays. Now, to kind of drive that point home a little bit more, we want to be able to track the requests going through complex distributed architectures that back these user-facing products. And end-to-end metrics allow us to do that. We can then also alert on any spikes in latency that we see, which then allows engineers to debug quickly before there is any measurable, visible client impact. Finally, we can also build service level objectives on top of these metrics. And an SLO essentially allows us to set a measurable target for reliability and performance. So we can say things like, hey, 99.9% of the requests should finish within 1 second. And then such a target can be tracked by engineers, managers, executives alike to understand how your system is doing. Is your system healthy? And then finally, these end-to-end latency metrics also help in the design and development phase for things like A/B testing. So with that said, I will come back to the example I just introduced, and I want to zoom into a specific sub-workflow, and I will use this throughout the rest of the presentation. Here, the stuff that you see circled in red is us going from messages into the Kafka queue, pulled out by the publisher service, and then pushed out to subscribers. So this is what the distributed trace corresponding to such a workflow could look like, right? I've got 3 main points in this workflow. You've got your consume queued messages in batches, process them, and publish them out to clients. Now, if you take a look at this top trace right here, you will notice these spans. You'll notice consume, process, a couple published spans for a couple different subscribers. You will also note something interesting here, which is that I've got this yellow arrow pointing to 2 different trace IDs. These are this trace and that trace. What's that? So note that we are pulling messages from this Kafka queue, which are representing some user requests, all together in batches by the publisher service. Then, the publisher service massages them and does something with it. So this type of pattern emerges a lot in high-volume queuing or batching systems where you've got like a bunch of requests coming together, and then They get processed and massaged downstream altogether. And this specific pattern is represented in trace through this little yellow arrow thingy that you're seeing here, which is called a link in OpenTelemetry lingo. And so that's what we see right here, what a trace, or 3 different traces for example workflow can look like. So now that I have shown you all an example trace, I want to take it one step further and equate it to a graph. So that's what we have right here. So a trace is essentially a directed acyclic graph. And you can think of every single span as a node in this graph. The directionality here comes from these child spans or child nodes pointing to parent spans or parent nodes. Each span or node is identified by, just for notation here, is identified by a trace ID, let's say T1, a span ID, let's say S11, and a span name, consume, which is representing what operation it was. So that's what we see here. And then again, you can see that this process node has 2 children. It's a commonly seen fan-out pattern in networking, distributed systems, and many things. And additionally, we see this process node have multiple parents, and that's a fan-in, which is, as you can see, quite literally the opposite of fan-out. And fan-in is what we just looked at as a link in OpenTelemetry lingo. All right, so I spent a lot of time talking about terminology and how we interpret trace as telemetry providers. I want to now talk about how our users, which is other engineering teams, talk to us about interpreting trace. So users can define what's called a rule, which essentially is able to identify an end-to-end workflow. So for example, we looked at that equity order execution management system. Oh, mouthful. And the team that is handling that can come to us and say, hey, get me the latency of requests going from consume to publish, so that I can then view those metrics in a nice time series on my dashboard, as you see right here. So they can come to us, they can say that, and they can be like, okay, I have a rule. Let's name it consume to publish. It's got a starting point, all the consume spans. It's got an ending point, all the publish spans. We refer to this as events. These points are essentially events, and an event just identifies a certain set of attributes matching a span. I know event is an overloaded term, so that's why I'm clarifying here. And then, you've got your start and end event within a trace. So that's how users can visualize what their end-to-end workflows are and how they kind of correspond to distributed trace. Okay, so now that we know how a user can talk to us and what a rule is, let's see what it would take to actually get the end-to-end latency from just one trace. Okay, so we have our trace T1, the example we've been working with so far. And in red, you will see the start event. In green, you will see the end event, consume and publish. The red path that I've highlighted here is representing essentially the path across which we need our latency, right? So how can I get that? Simply running a depth-first search through this directed acyclic graph, which would then also include this other path. And what we're trying to see is, well, hey, if we follow these different paths in the system, matching the start and end events, then we can get the latency between the start and end events. Because at that point, all I need to do is get the difference between the start of my start event, the end of my end event. So in this case, let's say path 1 had a latency of 3 microseconds, or path 2 had for 3.5 microseconds. Then these latency values can be aggregated into a nice little time series that you can then view on a dashboard. So to summarize all of that, to get end-to-end latency from just one trace, you can run a DFS and you can put that into a time series. Now, obviously, things are not so easy, and we don't just work with one trace. So how do we handle this at scale? So let's say this is what's going on. I've got this architecture diagram representing how traces are handled at scale. Essentially, we've got spans from all over our firm, from many different machines, coming into this ingestion Kafka topic. So this topic right here, this is not partitioned by anything in particular. Any span from a given trace can end up anywhere. Then there is a partitioner service. The goal of the service is to essentially put all spans from the same trace in the same partition. So that's why as you see here, these 4 spans, not together, 4 spans, all together now in the same partition. From here, we've got a service called Dagger, because it works with DAGs. That was my one pun for the presentation. And then the Dagger service is going to run your DFS, generate the metrics, and put them out on the dashboard. Easy enough. Not quite. So that does not really work because of what we just talked about. Drum roll, please, because of fan-ins. Why is that? As you see, there is a path highlighted in red here, right? So this is a valid path across which I want a latency. I want to see how long it takes to go from this consume to this publish. I cannot run a DFS across 3 different traces that are connected to each other if I don't have access to them in the same Dagger pod. And that's why what we need to ensure is that if you're a graph theory nerd, what we need to ensure is that all spans from the same weakly connected directed acyclic graph end up together. For the rest of this presentation, I will just call it a trace bundle. So all interconnected traces, trace bundle. So now this path, we want the latency for. This is a valid path. That as well, and so is that. So that's the problem we're trying to solve now at scale. So let me now go into 2 specific approaches that we took to solve this problem. The first one is where we aggregate trace bundles by rule. This is going to be a mouthful, and I will absolutely take questions later and talk about it in the hallway, but just try your best to follow. So let's consider this input Kafka topic. We've got this time the topic that is partitioned by trace ID. These spans are going into a service called Bundler. Bundler has 2-pronged goals. 1, put all the spans from the same trace bundle all together into one partition, as you see right here. Goal number 2, put all the different trace bundles that potentially match a rule in the same partition. So that's why you see that this Kafka topic is partitioned by rule. What do I mean when I say potentially match a rule? I mean that if a trace has just a start event, then send it into this partition, so it can potentially match it. And then Dagger will run the final matching with the end event and the start event, run the DFS, generate metrics, put it out onto the dashboard. If that did not make any sense, I got you. Let's work through this small example. Right? So I'm going to just zoom in on 2 different bundler instances. We're going to work with these 4 spans coming into the system. We've got a small Kafka topic, actually, which is used for doing just passing messages between different bundler instances for some gossip. Now, let's say that bundler 1 receives this consume span. It says, oh, that's a match. That matches the start event of the consume to publish rule. Then it looks at the process span. And it sees, oh, that's got a fan in. I've got these 2 traces that I don't have, but I do need to run my DFS on them. So what it's going to do is it's going to send some messages over to bundler 2 saying, OK, T1 and T2 are fanned in. T1 and T3 are fanned in. And T1 potentially matches the consume to publish rule. And by doing so, we can actually get a view. We can make sure that all bundlers have a view of all the trace bundles in the system at a given point in time. So they can all communicate this information with each other. And after they have this information, they essentially maintain these in-memory maps of these bundle and potential rule matches for these bundles. For the sake of time, I will not go super deep into this, but simply put, this allows us to identify that a given trace ID is part of a given trace bundle, which potentially matches a rule. And then I can use that to put them into the relevant Kafka partition. OK, so just to review, the key takeaways from this approach should be that we've got 2-pronged goals for our bundler service. Put all the trace bundles together, and put all the trace bundles potentially matching a rule in the same Kafka partition. so that we can then run the DFS across the entire set of weakly connected directed acyclic graphs. Now, to quickly summarize that, this approach works well when your traces match a small portion of, when your rules, match a small portion of your traces. So for example, if you had a rule that maybe included middleware spans that show up in pretty much all the traces in your firm, right? That would be a very heavy rule with a lot of matches, so that can lead to load imbalance in the Dagger pods. And this imbalance can be further exacerbated by fan-in blow. So not only do you have your traces, but you also have these fanned-in traces. So one downside of this is load imbalance for Dagger's memory. And so to kind of take this scalability one step further, we ended up exploring this other approach to kind of help fight the load imbalance issue. So this is approach number 2, in which we simply hand off what we call a partial DFS. So let's take a look. Again, you've got all your spans coming in from all over the firm in this Kafka topic partitioned by trace ID. This time, Dagger is going to consume straight from this topic. Dagger is going to be like, I'm going to start running my DFS, and oops, if I run into a fan-in for a trace that I don't have, I will just hand off information about my partially executed DFS to a different Dagger instance. And then we have a lightweight metrics aggregator layer. I will not go into that too much. And then we can, generate our metrics out to a dashboard. So to make that make more sense, very quickly, let's work through a small example. This time, I've got 2 different Dagger instances. We've got our 4 spans coming in. Dagger 1 and Dagger 2 also communicate with each other using a small Kafka topic. So Dagger 1 sees this publish span, right? It starts doing a DFS, and then it says, oh, wait, this process span has parents in trace 2 and trace 3. I don't have those. So what I'm going to do is I'm going to pass on information about the work I've done so far, being like, OK, this was the timestamp that I saw in the publish span. And I am working on a DFS for the rule consume to publish. So Dagger 2, can you please continue the DFS for me? And then Dagger 2 will continue that DFS for these trace 2 and trace 3s. One quick note, I recognize I didn't mention it before, but these DFSs that we're running them bottom up because naturally spans store their references to their parent spans. And there's a lot of nuance in there, which we can get to in Q&A if you want. OK, so that's kind of how this second approach works. Now, the second approach is more of a lazy approach compared to the first one, because we only send information regarding a specific fan-in when a DFS runs into that, when there is an actual match for a rule, as opposed to approach 1, which preemptively puts all these trace bundles together. And then this approach helps avoid the load imbalance issue. However, one of the constraints of this approach is if you've got really deep chained fan-ins, which means on one DFS path, you have multiple fan-ins that you encounter, which can then mean that many, gossip messages sent over Kafka and those delays. OK, so that was approach number 2. So just to summarize all of it, end-to-end latency metrics from complex traces can be generated at scale. We did that. It was very fun. But you should pick the best approach for you from operational knowledge as well about the traces at your firm. And end-to-end latency monitoring is crucial to ensure the best user experience in the microservices-driven world that we work in now. And finally, if you did not get anything else, distributed streaming DAGs are fun. And if you want to talk to me more about it, let's trace our way together. With that, we are done with the presentation. The QR code is for feedback, and we have time for Q&A. Thank you.
Hi, thank you for the presentation. My question is in relation to the bundler memory map that you referenced. I'm assuming it's either running on a dedicated virtual machine or a pod. In either case, if it goes down, how do you manage state?
Yeah.
Did you look into Redis as a separate thing that handles that memory?
Yeah. Good question. Answer, currently it's best effort. We would like to do something like having maybe like a write-ahead log, or you write to disk, or you write to a persistent volume. Right now, if it goes down, we do lose the metrics from that bit. So it's best effort for now. But yeah, that would be an ideal state we want to get to.
Thank you.
Yeah.
Hey, thanks for the talk. It's always great to see some real-world implementations. Question.
Sorry, I can't quite understand.
Sure thing.
Sorry.
Question on timing.
Yes.
So across systems, there can be time drift that happens, making just a simple start-end. Is that something that you've run into? And if so, how did you address that?
Yeah, so
Or
great
did
question. So for clock skew and drift, there are some systems that are more latency sensitive than some others. Those systems actually often, like some of those systems can't even use trace because they're like the network, like the amount of data you're sending over the network is so small, and they have like a lot of other constraints. So there are some super sensitive systems that will use their sort of custom solutions still. This does not quite handle clock skew. And I will say, there is actually a research paper, if you want to look it up online, on someone who tried to handle clock skew specifically with distributed tracing, if that's of interest to you. But yes, aware of that problem, we don't handle it in here, and the bulk of systems that do use this are not that like level of latency sensitive. Yeah. We have time. We have 4 minutes. Yes. Sorry. Oh, or I'll just repeat it. Go for it.
It's kind of along the other two questions, like in both problem scenarios, that the first one you have a hundred of one and the other one you have a dagger of one kind. So what is something is distributed under is there a message to the
Yeah, sorry. So yeah, let me talk a little bit more about these Kafka topics in between, right? So this is the dagger scenario. What they're using when they're sending these messages is this little Kafka topic. So in this particular case, we've got a small communication Kafka topic, which is partitioned by the trace ID of this like parent fanon. So for example, let's say I want to go to the Dagger instance that has trace T2. So I will send it into the partition for trace T2, obviously hashed. And then that is what Dagger 2 is already consuming from. So we are using a message queue, Kafka in particular, which is partitioned in a way that we know which instance is going to receive what. Okay. I could not understand. Sorry. Yeah, absolutely. No. We're not using trace ID as a topic. We are hashing the trace IDs into specific partitions. So for example, if you have like 50,000 trace IDs, you have like 5 partitions, and 10,000 are going into one partition. Yes?
For your rules that you're using with the developers, usually says like Kafka's message, storage, function, whatever. I mean, do you consider using attributes, spans, instead of filtering, baggage, or virtual form, spans that are on? Look at
We don't actually use baggage. It's something we are currently exploring. Historically speaking, it's because of having constraints on the amount of data we could send over the network to certain systems. So when users tell us what their like start and ends are, they can use span attributes also to like identify these starts and ends. They don't have to tell us anything more than that. We do have some like configurations like, okay, you can give us a hint. You can be like, you don't need to execute a DFS. You can do a simple match. Or you give me like the number of traces which did not meet a certain threshold of latency. But outside of that, just to identify these paths, all they need to do is give us attributes to define the start and attributes to define the end. That is correct. Ideally, we would have CI/CD time validation when your like critical workflows are changing, like instrumentation around that. But right now, it is very much in the hands of the user to inform us about it. Sorry. Take that question.
One question. The rules that you could use for filtering the partitions, is that based on text? Is it based on regex? Does it offer both?
Yes, tags, regex, and/or whatever, like your classic rule matching sort of logic.
Thank you.
Yeah.
And then why also give a metrics generator?
Yeah.
Did you look at using like span metrics generating?
So the key issue with that is, right, like with span metrics, they give you service-wide, operation-wide metrics. And for us, especially when you have a lot of these like pub submodels and queuing systems, you can't like easily have a top span that is like waterfalling and including your end-to-end time. So when that happens, you really do need to be able to get these metrics across different spans. And that's the part which span metrics often is not able to cover, especially when you're going across like different trace IDs and fan-ins. But yes, I would have loved to just use it out of the box. I am aware that we're out of time, so we can talk about any more questions outside in the hallway. Thank you, everyone.